Okay, so good afternoon, everyone. As I've been formally introduced, my name is Eran. I'm a senior software engineer at Intel. Specifically, been working at advanced analytic groups for the past 7 years or so. And today I want to talk about real-time deep learning inference on video streams, a solution we recently developed that support this. So a little bit about our group. Advanced Analytics at Intel, we do a variety of artificial intelligence and machine learning solutions across many Intel divisions. From the manufacturing process through the validations and up until sales and marketing, we have solutions or smart solutions over there. Some of our solutions are also encapsulated into products and deployed outside of companies as well. One such solution is in the health industry, where we help pharmaceutical companies collect data on Parkinson patients. And today I want to talk to you about a solution we recently developed supporting live video feeds and serving them with deep neural networks. And mainly this lecture would be about some architectural techniques that we used in order to make this low latency inference process. Let's talk a little bit about video analysis. So in general, video analysis has been getting a lot of attention lately. And as we see, there is a lot of research revolving deep neural networks which solve these problems very well. And there is also improvements in computational power that helps move these images and train those huge networks. And usually the problem that neural networks is trying to solve, or video analysis is trying to solve, is getting an understanding of the video, doing video analysis for video understand what we see in the video. And there are some core challenges in this field, and we'll review them quickly before moving forward. So be it segmentation or skeleton detection, the movement of joints, and even region recognition and detection of, as we can see in the Simpson episode down there. There are some also advanced features such as video captioning, meaning the video goes into the network and a full caption of what we are seeing in the video is shown to the end user. And since solving these core challenges will help a lot of use cases in the industry, such as autonomous driving, security, and many that you can probably think of, there are also many efforts in compressing those models that solve those problems and embedding them on edge devices in order to get fast, real-time inference on those networks. Our motivation was a little bit different. We were approached by one of Intel's divisions in order to automate visual inspections. One of Intel's labs is doing a validation process. Let's start from the beginning. Each of Intel's chipset go through, after manufacturing, a validation process. During this validation process, there are also visual inspections of live or dynamic system output that come from that chip. In this case, this testing lab is viewing, human beings are viewing screens that watch videos and trying to detect anomalies in those videos or defects in the screen's pixels in order to verify that the chipset is indeed okay. We're approached by this experiment, or testing lab rather, in order to, they said that they would place a camera where a human would usually stand and send out that feed so we can react in real time as a human would react and automatically identify those defects and anomalies in those pixels. So after reviewing those, or this unique use case, we came to realize that we had a few more challenges on our hands. The first one is different defects in videos or in those dynamic system output can come from very different worlds. And while a human can in one test identify many defects, we would probably, and this is actually what we practically saw, would need to deploy many deep neural network models in order to identify different defects. Another thing was, while trying to understand the video, let's say you want to detect entities on a video. So if a car is driving straight, then, or even if it's not driving straight, in a few milliseconds it will still be a car. So maybe you can downscale the video a bit in order to get better performance and lighten your computational efforts. As we were expected to detect anomalies as well, which could be very short in time, we could not enjoy this smoothness of video, and we needed to process each and every frame at 30 frames per second. So as you can understand, these problems are quite unique, and we are also requested to join an existing process and not deploy whatever equipment we want in the testing lab. So we would need to receive those frames as a video feed to us, analyze them, and return an answer really fast. So we have decided to develop a noble architecture that would centrally serve, instead of deploying on edge devices, centrally serve those video feeds, those deep learning models with focus on low latency. And I emphasize low latency because usually when we're talking about, mainly in training, deep learning, we are talking about getting the highest throughput possible from our resources. But our focus, and this is what our architecture supports, is on getting the lowest latency possible, not the highest throughput, but the lowest latency for a given throughput of frame rate. And not the lowest latency possible for a single frame at a single moment, but lowest latency possible across the entire infinite video feeds, one frame at a time, without getting delays as time passes by. So for instance, let's look at a simple use case of what our solution can do. And this is just for illustration to understand what we're talking about. Then we have several cameras across the testing lab, and they are catching frames at approximately 100 frames per second, sending the frames back to our server. The server takes each one of the same frames, or our solution rather, each one of the frames, push them through 3 CNNs, 2 LSTMs, and then there's a reasoning process which take each one of those 5 results for each one of those frames and ensemble final results to be shown to the user. Here the user will be shown that one of the frames will find defected or have an anomaly in it. We're able to do all this process on a single server actually in less than a second, and we are able to get this sub-second latency since our architecture supports using the lowest possible inference time for each one of those models, as you will soon see. But deploying such a solution did not come without any architectural challenges. So let's review those as well. So first and foremost, the most hard thing to do is the CNN, mainly the convolutional neural networks are very hard to compute, and now they are part of your critical path. So we needed to know how to handle this, and you are expected to react in real time to have a fast turnaround. Another thing is, if you're thinking about batching in order to better utilize your resources, better vectorization of the computations, then waiting for a batch to fill up in order to better utilize your resources will actually make your latency go up, and this is against what we wanted. So we need to think about a mechanism that would use this batching, but not get our latency up. As I mentioned before, also we had a variety of models, meaning we need to do all this in real time with a few different models and ensemble the results or get some reasoning process together and all this in this real-time world. And last, as in any system, this system needs to be scalable, meaning if tomorrow we need to serve more video cameras, then we should be able to do so just by deploying more resources. And the question here was, if you batch naively, then when do we scale? Because if I am waiting for a batch to fill up, then my resources are idle. Then, when I serve it, the resources may reach 100% utilization. So when exactly do I scale? So answering all these questions, and without any further ado, and this is the part we're going to dive into the architecture. We call it internally Archelon. It's a scalable, fault-tolerant, and fully asynchronous serving system. And in high level, it's fairly simple. It has 4 main components. It's got the API, the data store, the application, and the model. Down at the bottom, we can see the critical path. Frames go through the API and saved into the data store. End user pulls frames from the data store through the API back with results. Nothing special happens here. Above the data store, we got the application and the model. This is where the magic happens, so to speak. Application pulls frames from the data store, which are waiting to be processed, sends them for inference in the model part, and this separation is very important, gets the response and save the final results back to the data store. Now you can think of the application part as a collection of asynchronous processes, and you can think of the model part as a collection of microservices. because this is exactly what they are. And this separation is really important, not to embed the model logic into your application, as this will make you much more scalable, and as you will soon see, also supports the low latency part. And frankly, the most important part, or the most interesting part, I believe, is the application part. So we're going to start talking about it. It's a collection of asynchronous processes, and this is our basic processing unit. We call them AIUs, or asynchronous inference unit. These units are always on, always looking to process frame, always using the resources. Constant resource utilization, which we didn't have if we were waiting for a batch to fill up. So this AIU is looking into the data store, which frame do I need to process, pulls whatever frames that needs to be processed, does some pre-processing, sends them to the its respective model, microservice model, in this case TensorFlow, gets the response back, does some post-processing, and save the final result back to the data store. Now, while it was working, some other frames got aggregated in the data store, so it looks back into the data store and pulls whatever frames got in there and does the same process over and over and over again, constantly working. As you can understand, this creates this phenomenon of dynamic batching. The batches changes, but if we have constant throughput, then usually, or this is actually what happens in practice, this batch size converges to this constant size or constant range that will get you the lowest latency possible for serving that specific model. The AIUs are also stateless, meaning any state they hold in the data store, which by nature makes them very scalable and extremely fault tolerance. On top of these benefits, we have two additional benefits of working with AIUs this way. The first one, which is actually my favorite design pattern, is separation of concerns. We can dedicate an AIU for each one of our deep neural network models, meaning if we have two models, it doesn't matter which framework we use to write them, as they are simply microservices. We'll spin up an AIU for a ResNet model and spin up an AIU for an object detection model. One AIU would probably converge to the best batch size to get the inference as fast as possible from ResNet, and the other one the same from the object detection part. So that's really big benefit. Now, if the AIU, which is working with ResNet, needs a little help, we can since the AIUs are very scalable, we can simply deploy another AIU that would help him, let's say, reduce the batch size a little bit, maybe help him with the pre and post processing, or even better utilize the resources. Another interesting benefit is the AIU is also agnostic to the frames that are coming in, which means it doesn't know which stream it came from. So it can batch together multiple video streams, meaning actually it uses the batching mechanism in order to lower the latency, get better inference time for multiple streams. Of course, we hold them in the data store differently, but the processing is done by the same process, or by the same processing unit, rather. The question still remains, so when do we scale? While this was a hard one to answer when the GPU utilization was fluctuating, it just became a little bit easier to answer if you're using AIUs. So as we noticed that our criteria are kind of converging to this constant range, mainly the batch size, the latency, and the resource utilization. So all that was left to do is to decide, according to operational need, when do we want to scale. If we want to get the best or the lowest latency possible from our resources, then we'll probably scale only when we're out of resource around here. But if we do care about the latency, so we'll set some latency threshold, and we'll probably scale here and add a little bit more resources here in order to keep the latency low. So that's about the application part. The second thing I want to talk about is the data store. Just as a reminder, the data store is in the middle. It's kind of our mediator between things. The entire thing is asynchronous, as you can understand. So we need a place to synchronize things. And the data store does exactly that, and that's its first attribute. We have used the Redis as the data store, and we've implemented the implementation part is quite like a queue management platform. Everything is a queue. There are entities that go into the queue. In this case, we talked so far are single frames. They are pushed into the input queue, then they are collected and pushed into intermediate result queue, and then the reasoning process takes them from that queue and moves them to another queue until the process is done and the frames are pushed, or the result rather, are pushed to the final results queue. These entities that move from queue to queue, they not need to be only single frames. They can also be ordered sequences of frame, meaning we also support sequences in this exact same architecture, so we can support LSTM or other RNNs that need some kind of sequences served to them. The second part, or actually the last part in the architecture, is the model. And usually when you ask someone, how do you serve your model in production? And the answer is, well, I use TensorFlow to train it, so I serve it with TensorFlow, or TensorFlow serving for that matter. So that's what happens. And if we look at how a TensorFlow model would be served in our architecture, then the AIU would pull the frames and it needs to send them to a microservice of TensorFlow serving. But that means that the AIU needs to know how to speak gRPC and knows protobufs in order to communicate with the model, but the AIU is asynchronous and also needs to be agnostic and decoupled from the modeling part. It does not need to care about which technology was used in order to implement the model, because this can harm it in scaling later on. So we've decided to develop another layer that would decouple them both completely. We call it a model service that has a common API on the one side facing the AIU. So the AIU only needs to know how to speak with that model service. And on the other side, the model service has a generic client that knows how to speak HTTP, gRPC. If it needs to use protobufs, it uses protobufs, and making the AIU completely agnostic of what's happening on the other side. The AIU can consume this model service as a Python package as well as a microservice. So to conclude the architecture, I want to go through an entire Dataflow, which is a little bit similar to what we recently deployed in one of our labs. So let's say we've received from our data scientist a few models, in this case LSTM, object detection, and ResNet, and we need to ensemble the results or get a reasoning process. So we deployed 3 microservices, TensorFlow serving in this case, and then spun up 3 containers with AIUs. And the first one just pulls ordered sequences from the data store, does some pre-processing on them, sends them to the LSTM model, does some post-processing, and saves the respective results back to the data store. The second AIU does exactly the same with single frames for object detection, and the third, the same for ResNet. Then the reasoning process, which is exactly the same as an AIU, just doesn't send things for inference, always looking for intermediate results in the data store, looks for intermediate results. In this case, it found 3 results for 3 frames and does some assembling process, some reasoning. And let's say for sake of argument, it does an OR condition between all the results and save the final results. In this case, 1 frame was detected as a defect back to the data store to be shown to the end user. To conclude, I want to give a few more general suggestions in order to reduce latency, which we used on top of our architecture. They are quite straightforward, but we found them very useful. It's very weird that I cannot see you, I must say. It's just trying to get used to it still, yeah. So first of all, if you can receive a smaller image, and this is really important, receive as smaller image as possible, meaning the biggest one you need in your models. Because as video streams are in high def today, neural network models do not use high definition images usually. The biggest one I've seen mainly is 512 by 512, so just ask the end user to send you a smaller image. If you cannot do so, then as soon as you get the image, resize it, preferably using a CPU, and save it back to the data store. So you will not carry a big image around all the time. Now, the second thing is separate the presentation from the predictions, meaning you do not need the image with you. If you do not need the image with you for your computation part, then don't take it with you through the asynchronous processes. Just do the processing, save the image to the Datastore, and attach the prediction at the end. Another thing is use your resources according to need, meaning try and see which resources, CPU, GPU, TPU, whatever resources you have, check them before you decide on a resource that you want to use to get the lowest inference time as possible, and then use it. And the last thing, implement the best serving method you can for each model. If you're using TensorFlow, do yourself a favor and use TensorFlow serving, and don't try to serve that model not using the serving layer of TensorFlow, because it would probably work a little bit slower. So this was our asynchronous architecture, and I was Eran, and now I'm open to questions.
Okay. Speaking about latency, do you pick and choose which frames do you want to process? For example, even if you have 60 frames per second, maybe you only need 10 of them, right? And then if you don't get enough, maybe you need 20 or 30 or 40. Do you have some kind of processing like that in matters of like how much to sample? Sorry.
I'm sorry. We actually process them all. We have to process them all since there are some phenomena that are really short in time. So we need to, each camera sends us 30 frames per second, and we process the entire frame. And this is actually one of the obstacles, that we could not downscale the video frame rate.
I understand that you analyze mostly frames, right? Not like real video. Am I correct? Like, does this video has a state that you need to monitor that affects the classification or regression or whatever problem you aim at?
I think I understand. We do analyze frames. We do also analyze sequences of frames in LSTM models, getting the, let's say, context of the video, because some defects have been identified better using windowing, so to speak, if that's what you meant.
Yes, thanks. Okay.
Do you have initial results against the human observers?
Actually, yeah, we continuously checking our results, and they are good. I don't have the numbers with me, so I don't want to invent. But they're good. This product is moving on to the production line, so they have to be good.
So in your architecture, the model is not part of the Docker container; it's outside of it.
Yeah, I didn't mention it, but since everything is asynchronous and everything is a microprocess or service, then we pack everything in containers. So everything is in a container. Whatever you saw is in a container.
The model also?
Yeah, the model also.
So it's in a different container than AIU, or it's in the same one?
Yeah, different containers. Because then it gives you the ability to deploy several containers of the same model and put a load balancer in front of them to get better scaling, or if you want to scale just the AIU and not the model, for instance, gives you good separation of concerns.
And what is the communication between the AIU and the model?
In TensorFlow case, it's gRPC, because that's what they use. And we can use simple HTTP, because I'm doing like this because nobody else has a real serving mechanism for deep neural networks rather than Google. Everybody, you just need to load your model, pack it in some kind of service, then you probably use HTTP microservice.
Did you measure how many times the frame gets copied in memory?
Actually, we know how many times. And currently, our use case, we have, I think, it's ×2 or ×3 copied in memory. That's about it. But it depends on mainly if you think about it, if we need to support different queue sizes, then we need to probably duplicate the image in different queues. one queue of size, let's say 1 single frame, the other one, why am I doing like this? The other one is a queue of size 10 and the other one is queue of size 20, then we need to duplicate it 3 times. So that's about it. So when we pull it, it will infect the memory. But
So each queue has a certain size, like a certain batch size? Is that what you mean?
it's not a batch size, but it's a more, let's say, broad question, but it's a sequence size. If we need to support a model that needs a sequence as an input, then we need to save those entities in Redis as sequences. But if we only need to process 1 frame at a time, then we save it as a single frame.
That's from camera till result, 2 to 3 copies? 2 to 3 copies from camera?
It really depends on the use case. So
Right. Well, that's what you meant.
the basic use case, we would not duplicate it. It would only be 1.
All right.
But it depends on the model.
Thanks.
Thank you very much.